right. So welcome everyone. Today is is going to be the last lecture. So as I said, the plan for today is I think we are going to wrap up the the topic that we were covering last Tuesday, and then we are going to describe some of the let's say big directions that have not been covered here, but mostly like open problems. And then it will be good to, as I said, if you can just do like a round of table where you can describe a little bit what are your, let's say, what is the thing that you like the most from the class, and maybe if you have any project or any plans about doing research in this topic in this area. All right. So okay, so let's recall from last Tuesday. We saw the scattering transform on the translation group. The translation group. And that was obtained by essentially composing 3 building blocks. So remember, we had this AJ of X, which is just a convolution with a low-pass filter. Then we had these bandpass filters, which were a collection of wavelet filterings, where lambda was in a certain set of scales and orientations. And then we have this nonlinearity that in our case was just like the absolute balance modulus. Okay, and so by defining the kind of the composition of the wavelet with the absolute value, we can define, if you want, this operator that is just M with WJ. So it's just a collection of this wavelet modulus. Then we are in business. Why? Because the representation was doing was going from X to first doing the low-pass filter, AJ of X. Then I would do UJ of X with AJ. Right? That was so that, remember, that was like a scattering coefficients of order 0, coefficient of order 1, and then every time we apply a low pass and AJ, we combine, we complement it with the bandpass filters obtained by the wavelet. Okay, so basically now we would just do UJ times UJ times A of X, etc. Okay, so these are like second order. Etc. Okay, and we saw 2 main properties, right, on the scattering transform. We describe two main properties. The first one was the deformation stability. So if phi of X was like the collection of all the scattering coefficients for P that is in this set of all coefficients, then we have the following result. This is sorry, for P that goes up to order M, right? So basically, in the previous description here, I think that you take all the coefficients up to a certain order, right? So you repeat this process a finite number of times. Okay, that's the number of times that is M. Then we had this following result that the coefficients of the image and the coefficients with the deformed image were satisfied inequality, of the form. This depends on the number of layers times the norm of the sigma of x times the deformation cost. Right, and so this is in big contrast with the Fourier modulus. Okay, so remember that the Fourier modulus we saw a couple of lectures ago that it didn't satisfy the stability problem. So that was deformation stability, and then we also described energy conservation. So that was the property that if I define the norm, it was it's x, by definition is the sum for all the paths of this L2 norm. Then under an appropriate choice of wavelets, so they needed to be unitary, if you remember. We have that this representation preserves the norm. Okay, which was it's always a nice acute thing to have a representation that is kind of doesn't change the norm, right? The ultimate. Okay. So, like the questions for today, right? So, like remaining questions for today. So, we describe, well, how does the energy conservation impact or relate to information content, right? So, what is the basically information content? Or the what we call it discriminability. Ability of the representation. Other questions that we are going to describe today is how can we extend it beyond the translation group? And also, of course, is there a way, is there a bridge, natural bridge from the scattering to the maybe things that are more familiar to you, the CNX, to convolutional dynamics? Okay? All right. So for this, as I said, so remember, like the starting point, right, from this question is that energy conservation is not the same as information conservation, right, or information. I write it like this, but the idea is that, in other words, we don't have the inverse scattering that basically S minus 1 that would take the representation and go back to X does not exist. Okay. there is uh, there's several ways where you can convince yourself that this is it's a fundamental limitation, like obstruction. But somehow it's part of the game, right? Like we are here, we're not in the business of preserving the information in X. We really want to extract useful information from X, right? Doesn't mean that we want to reconstruct everything. And so where does this loss of information arise, right? So what is this part of the process that is lost? So if as I told you before, just also try maybe to make sure that people are not completely lost. So if I have this mapping that you take any X, so from L2, and you map it to this family of convolutions. So you first extract the low frequencies with your lowest filter, and then you compute all the wavelet coefficients. Let's call this mapping, let's call it T. So question for you. Is T invertible? Under our, let's say, usual assumptions. And how we define these wavelets. So who has some opinion? Do you think this is already are we already doomed in the sense that even the first step of the transform is already non-invertible, or is this operation still keeping all the information? It's just like a binary. What do you think? Yes or no? It's okay to be. I mean, it's okay to be wrong.
I'm going to be wrong, but I will guess it's invertible.
Yes, of course. Yes, and let's. That's very good. Thanks, Victor, for taking the lead. Yes, of course, it's invertible. And remember the condition we were using. So remember that we are manipulating this Littlewood belly transform. Littlewood belly condition, right? So, so remember that this Littlewood belly is telling us that for all frequency, right, we have the following inequality. J R theta psi squared. Okay, so remember what is this? What was this inequality saying us? Right? This seems like a weird. I mean, it seems that a little bit disconnected from the actual transformation. But this is just telling us something about the singular values of this matrix. Right? Think about this T. T is a linear map, right? It's a linear operator that maps a function to a family of functions. But as a linear map, you can just, compute its spectrum, right? You can look at the singular values of this map, and because these are all convolutions, right? So every of these output, all the outputs of this map are convolutions. So if you want to understand the singular values of this map, naturally you want to look at it in Fourier, right? Because this is where all the convolutions are becoming diagonal. So this is exactly what this Littlewood belly condition is telling us, is that there is no. If I look at this transform in the Fourier domain, right? I could now plot. First, I could plot the Fourier transform of a low pass, right? That is something like this. That would be the Fourier transform of the low pass filter. And then I have, for every one of my wavelets, I have some Fourier transform that, of course, as I change the scale, this Fourier transform is going to change, right? But the picture that you should have in mind is that the finite scale is going to have some spectrum that is like this, And then as I start to make the scale broad, coarser and coarser, right? The spectrum of the Fourier transform is going to kind of tile the frequency domain like this, right? I'm just plotting it in 1D, but you get the idea for 2D. So basically what it means is that together, they are creating a very nice regular tile of all the frequency domain. So which means that every signal, any signal input is going to be able to reconstruct, because I can, together they are able to actually recover all the frequencies, right? So there's all the frequency information can be extracted, right? And formally means that basically the smallest singular value is away from 0, which means that the matrix, the operator, is non-singular, right? So it means that I can invert. Okay, so this is really, yes, right? Of course I can invert. That was Q0, right? Then there's a Q1. And now I'm going to make the game a little bit more interesting. So I'm going to go from the operator T to the operator, let's call it T tilde, right? Which goes from X. Now I'm going to have the same low frequency. And now I'm going to remove the phase of the wavelet transform, right? So I'm going to just look at the modulus of these guys, right? And I ask the question again, is T tilde inverted? What do you think? It's a similar question. But now the difference is
I
that
think no, it's not.
Okay, so that's actually a good intuition, but it turns out to be wrong. It turns out to be wrong, right? So in fact, let's think a little bit what this means, right? And actually, this is a little bit related to the question that Kai Zite put on the chat. Okay, so here let's count the number of pixels, right? So X, let's say that X is an image, right? That has n by n, right? So it has n squared pixels. Here we're mapping it to a collection of images, right? So every one of these channels is an image, right? It's like the convolution doesn't do any subsampling, right? So there's really no subsampling happening, right? So I have the output here would be, keeping these colors. Let me just, do something that might make it easier to map it to the previous thing, right? So I have different colors, right, for the different channels. So here I would have the same, right? So I would have one image that would be the low pass, and then I have a bunch of other images, right? So one for every output of my model, right? So this one, I would have this one here, right? One for every subband of my wave. Okay, so this is like this would be X convolved with J. This would be absolute value of this guy. Okay, so here we are really in the business that if let's say that right, so we go from n squared to n squared times lambda coefficients. Right, and now what is the question of inverting? Right, so what do we mean by inverting is that suppose that we know, so suppose we know y, that is this T tilde of X, right? So y is a vector. You can think it as a vector if you want in the finite case of n squared times t, right? So I have all this number of coefficients. So we want to find X, right? So we're going to solve X in this system of equations, right? In y equals t. So this is actually a system, right? Of n squared times this number of subband equations with how many unknowns we have? We are looking for X, right? And X has n squared pixels, right? So there's n squared unknowns. Okay, these equations are nonlinear, but still, yeah, thank you. So, but still I have many more equations than unknowns. And I know there's one solution, right? I know that these coefficients y, they really come from some x. So the question is, when is this equation going to be determining the single solution, right? So when is this system of equations going to have a single solution that is x? So the answer is that very generically, the answer is yes, right? And this is really related to, I don't know if you're familiar, this problem of what's called phase retrieval. Phase retrieval is a fundamental problem in many areas of computational math and signal processing, which is, for example, used in a spectrography, right? Like, or even if you do like some kind of like IRM, right? So typically, many physical phenomena, when you wanna learn something about the structure, like a molecule or a crystal, even like I think some parts of the human body, you cannot compute things directly, right? You only compute amplitudes, right? Like in a certain Fourier transform, you can basically, the goal is to recover some structure out of measurements that look like this, right? They look like the phaseless measurements under some transform. And so this is actually an important problem. And here, what is kind of helping us, right, is really the fact that we have this over-parameterization, right? Like that we go from n squared coefficients to much more than n squared, right? The transform is very redundant. And so the redundancy of the transform is kind of like overcoming the nonlinearity, right? The fact that, yeah, coefficient by coefficient, we are throwing something, but we have, because we have so many redundancy, we can afford to throw stuff, right? That's the way to think about it. So that's Q1. So wait, now you must be saying, wait a minute. Each one of the scattering, right, was built, right? So but the scattering, right, S of x, if you remember, it's built by composing a bunch of these steps, right? We basically, what we do is that we take this operation, and then each one of the outputs of this t tilde, we apply t tilde again, right? And we keep doing this many times, right? So basically, it's built by applying t tilde repeatedly. So t tilde is invertible. Doesn't this mean that S is invertible? Okay, so I'm building this scattering by applying this operation again and again and again, right? And I can invert, and every one of these things is invertible. So why is this? So now, as the question Q2 now, is this S invertible? And so the answer, so like in this time, the answer here was yes, right? It's invertible. But now the answer here is that it's no. And the reason for that is stability, right? So if you there's one little detail, right? When we think about this transform, is that in this t tilde, there are a bunch of coefficients where there is no low pass filter, right? So here in this operation T, right? There's one part of the coefficients that are the low pass, but there's another family that are not low pass. Yeah. Whereas if you remember in the scattering transform, right? Like when we define it, that was defined. It's not here anymore, but if you remember from the definition, right? So remember that S of X is just a family of all these like concatenation of applying lambda 1 to lambda 2 up until the last coefficient. But then I always end up with a low path, right? For all the paths in a certain space. Okay, so basically the last step, so it's almost like I'm repeating this operation, but there's always like a boundary condition that is slightly different, right? So I'm missing always in the last step of the scattering transform, I always arrive at low pass filter, right? I mean, this operation has to be in every one of the coefficients. Otherwise, all the stability property of the transform is lost. Okay, so and because this transform, this mapping here is the tilde, this might be invertible, but the inverse is very unstable, which means that slight error in the, if I lose a little bit of information in the output, the transform is no longer invertible. Okay, so that's in a sense what is behind this problem, right? Is that the scattering transform is not invertible, but it's very, very close to being invertible. Just because the reason why it's not invertible is this fact that there's a truncation, right? There's a loss of information at the very last step. Okay. All right. Of course, let me just say that in practice, if you're interested, so let me just put a remark here. While S is formally, like strictly speaking, but invertible, we can still consider the following problem. The following program, and this gives like a decent result. We can still the following problem, which is to minimize, so given some coefficient, right, given y, that is s of x, for x that is unknown, we can minimize over x prime y minus s of x prime. Okay, and this is a very natural problem that, of course, if s was invertible, would give as a solution the only x that is in the pre-image, right, which is the one that we are looking for. But even if it's not invertible, you can still consider it. And this has this model, like this gives some kind of like a soft inverse, right? So here, basically what we are trying to do is geometrically, right? So if you think about what this is happening, right, is that here we are looking at all the, so this is all the x's, right? And here we are looking at maybe some set of x's, right? So these are all the x primes, such that s of x prime is equal to y. Okay, so if a function is a mapping is not invertible, well, you can still associate it a pre-image, right? You can still consider all the points in the input that map to a certain output, right? And so what this algorithm is doing is that, okay, maybe, this is not sufficient to identify the exact point that I want, right, that I used to, that I started, but if you give me any point in that set, that might still have some properties that resemble X in the thing that I care about. And this is what is exploited in many empirical papers, right? So we have a few papers if you're interested in this. So again, there's a tutorial. So for more information on this topic, check the scattering book chapter. I believe it's referenced on the website. Okay, so there are some interesting numerical applications of this algorithm. Okay. There's another thing I wanted to talk about beyond the inversion, is that especially for those of you who have already been that have been reading or like manipulating convolutional neural networks, you might try to understand, okay, what is the things that are similar and different between the scattering transform and convolutional neural networks? And so there's one thing that is very different, right? Is that if I think it in terms of an architecture, well, like what is the connectivity between the input and the output, right? So in the scattering, so I can just look at the scattering versus seeing. Okay, so in the scattering, I have my x, and I start by applying a filter bank, right, like a convolutional filter bank that has different channels, if you want, right? Each one of these channels is a convolution plus a nonlinearity, and then I repeat each of these outputs, right? I compute again the same transform, right? The same transform is just taking this thing and retransforming it again. And this thing is retransforming it again. And this feature map is retransforming it again, and so on and so forth, right? It's like and this operation is the one that we just wrote here, that is this like t tilde, right? Or I think I called it u also before. Okay, so it's basically computing the wavelet coefficient, wavelet convolution followed by a absolute, like a modulus. In the CNN, right? There's something slightly different, right? Is that you have x, typically, sorry, in the CNN, typically you write it like this on original, so you have some input x. You apply a first family of filter banks, right? That is giving you a family of filters of images that are stacked, right, like this before. And so here, instead of so this is just like at the beginning is the same thing as we have here in our case. But now, the difference is that instead of now in the CNN looking at each of these slices and breaking it again with the tree as we do before, we will recombine everything, right? So basically, there's a model that recombines. Let me just write it in maybe a different color. So there's what we call is like a recombination, right? Across channels. Okay? Because before going to the next level, right, you recombine again, then it starts combining the same thing, but you see that the difference is that instead of treating every one of the feature maps as a similar as the input and then applying the same operator, it's an operator that is still convolutional, but it looks at the joint, right? It looks at all the channels at the same time, right? So basically, instead of treating each of these leaves separately, you combine them together. Okay, and so the natural question, right? So basically, is what is the impact of this separable? Okay, so having this separable architecture, in many respects, it seems like conceptually simpler. So is there like a downside? Is there like a price to pay for this very particular simplified architecture? So for this, we need to now study like a different concept, which is the notion of a joint versus separable grouping path, right? And this is what's gonna give us the insight of what is the cost, what is the impact of this separable architecture. Okay, and for this, we are gonna let's try to look at the simplified side. So let's consider like a group G that I can write as a product. In that case, it's something that is called like a semi-direct product. It's written as some kind of a fancy, it's like kind of a funny looking cross. It's like something like this. And it's 2, which is called a semi-direct Now we are going to see what exactly what this is. Like it's a semi-direct product of two groups. Okay, so what this means, it means that basically what I'm saying here is that G1 is a normal subgroup of G, right? So this is another way to say the same thing, right? So this means that G1 is a group, and that the quotient, like the quotient group, is also a group. Okay, so I'm factorizing a group in a way that each of the two factors themselves have a group structure, right? That's what the semi-direct product means. And so we are going to give an example just to make things a bit more precise. So basically it means that any G in G, right? I can think it as G, I can think it as a product, as something that contains two elements, right? Like from this is Gi in G. So let's look at an example of this factorized structure, which is the G, which is called the Roto translation. Okay, so G in that case is going to be written as R2 semi-direct with SO. Okay, so basically what I'm considering is if I take the plane R2, what is the group of transformations that consist in a shift and then a rotation? Okay, so you can see that the way you describe these transformations, it already means that you are combining two blocks, right? Like one is the translation part, and the other one, the other one is the rotation part. But as you can probably convince yourself, these two operations, they are not commutative, right? They are not completely separable. Okay, so for example, so if I take, I can parameterize this, like one of these elements, right? So basically, this is an element v1 alpha 1. So this is the shift. This is the angle in which I rotate, right? So any transformation, I can parameterize it by what is the offset that you apply, and then what is the angle in which you rotate. Okay, so if I combine these two operations, right? So you can convince yourself. If I take one of these elements of this one of these transformations and I compose it with another transformation, I still have a transformation that is a combination of a shift and rotation, right? So the roto translations form a group. And how can I write the resulting object, right? So what is the effective shift that I see when I compose these two things? So you can see that it's not, this is not V1 plus V2 alpha 1 plus alpha 2, right? That's not true, because the shift in one transformation interacts with the rotation of the other, right? So the right way to combine these two things is to say that I have V1 plus the rotation of alpha 1 times V2, and then alpha 1 plus alpha 2. Okay, so really, this is the best by far is that you try to do it in your paper, right? A piece of paper. See what happens if you apply a shift, like a translation plus a rotation. Okay, so you can see that there's no abelian structure. So now the question for you would be, okay, now I would like to build a representation that is invariant to this group, to the roto translations. And you look at this and say, okay, but wait, if this roto translation group looks like a product of translation and rotation, can I somehow take a representation that is translation invariant, another representation that is rotation invariant, and combine them somehow to build invariance to roto translations? Okay, so the question here is, can we build invariant representation with respect to G from invariant representations with respect to its factors. That would be great, right? Because this gives you like a very, it's like this, like, this area of algebra, like a, group theory. It's like groups are kind of these building blocks, right? So if you understand how to do things with all the small components and you can combine these techniques together, you can essentially understand how to build these invariants for anything, right? Because you understand how to do the building blocks and then you can extend. So let's suppose, like specifically, suppose the following. Then I have a representation phi1 that is a G1 invariant. And I also asked it to be G2 equivariant. And then I have phi2 that is G2 invariant. Okay. So now I claim, then let's consider phi, which is the composition of phi2. Okay, so if you think it more in the kind of a diagram kind of style, right? You have some input x. You think that you have two transformations, right? You first apply phi1. And so the idea is that if you have some group that is acting here, right? If you have some group that is changing your input, you might kind of kill the action of the group in two steps, right? In progressively. This block is going to kill one part of the transformation, fraction of the transformation that is acting, and the other part is going to kill the rest, the remaining. That's the intuition. And so let's verify, right? So let's verify that if you have a transformation, right? So let's compute phi of the action of G that is acting on X, right? So you take any G that is in G, that remember that is this G1 semi-direct product of G2. Okay, so we can think about this as, remember, by definition, we can write it as the G1, G2 acting on X, right? And this is by definition is phi2 or phi1 of G1, G2 acting on X. Okay, so now we apply the first property, because phi1 is G1 invariant. This is the same as phi2 of phi1 of G2 times X, right? Because the part that involves G1 is not seen by phi1. Okay. But phi1 also has equivariance with respect to G2, which means that it commutes with the action of G2. And so because phi1 is G2 equivariant, this is the same as phi2 times G2 times phi1 of X. And now you see where we're going, right? Is now we apply the invariant of G2 of phi2. we get that this is the same as phi2 of phi1 of x, which is phi x. Okay, so we end up at the result that phi1 of x, sorry, the phi of g times x is equal to phi of x for all x and for all g. So a priori, we can build larger invariants by composing simpler invariants or equivalents. Okay, but does this seem like a little bit too good to be true, right? So is there some kind of like a downside of this problem, right? So it seems that, you know, life is easy, right? By just understanding, like if you give me a complicated group of symmetries, if I understand its factorization, right? If I factor this group and I understand very well how to build invariants with respect to each of these factors, then I'm done. But is there a downside? Stability, good. That's one possibility, that which is certainly possible. But there's another. Remember when we discussed about these properties, there's always two things that we put in tension, right? Indeed, there was like invariance, or kind of an extension of invariance, generalization of invariance is a stability. But then this thing has to be always in tension with the ability to have a rich representation, right? So that you don't want to throw information, right? You want to be invariant, but you also want to be powerful, right? You want to capture all the intense, interesting information that is in the input. So in other words, is there a risk of losing information when you take this factorized approach? And so indeed, that's what happens, right? There's a loss of discriminative power. Okay. So let's try to convince ourselves that indeed there's some downside. There's a cost of doing that. Okay. So let's give an example. Let's think about maybe the best just to show an example. Okay. So think about like an example of images again, and let's say that you want to have some kind of like a digit recognition, right? So the natural group, right? Think about the group of translations in the play, right? So think about like translations in R2. But the translation group in R2, right? Let's call this a G, right? So you agree with me that I can take G and factorize it, right? So I can always express a translation into D in terms of a translation in horizontal and translation in vertical, right? So G factorizes in that case as a semi-direct product. In particular, it's a direct product, which is like a particular case of a semi-direct product in terms of G1, G2. And these are the vertical and this is the horizontal translation. Okay, so so now you see where this is going, right? Is that I could take a model, like a representation that looks at the horizontal translation and treats the horizontal translation separately from the vertical translation, right? So, for example, I could take a representation that goes at the input, and now because the horizontal translation only acts row by row, right? It leaves each row, it leaves its invariant, right? Like because the translation is never going to be on the horizontal translations by definition keep the rows invariant. So I could just say, okay, why don't I take a representation that I'm just going to look every row separately, have a representation that is invariant to translations in the row, and then I take the output of this thing, right? So basically I have like a row by row invariant representation. So basically, sorry, shift invariant. Translation invariant. So now I have a vector of coefficient, right? So this would be like if I think about x, so the first row I'm going to call it x1, x2, and xn. Now here I have like a first representation. I call it phi1. So this would be phi1 of x1. Well, let's call it phi row, right? Just to call it identified with rows of xn, right? So these are numbers, right, that are invariant representations of every row. And now that I have this, I can follow my composition from before and apply now like basically an invariant representation, like basically now it's like a column. So now it's like another translation invariant representation phi c, right? So I can just now phi c of all the phi r's. So indeed, I can verify that this by the argument that we had here before, right? By these arguments, this is going to be translation invariant, right? This technique. But can you see the problem of this representation?
Yeah, you lost the power to discriminate numbers, no? You could have
Right,
a 9 that is similar to a 1 in this representation.
Well, indeed, you can think, what are the things that I am allowed to change in my input that are not going to change this, right? This phi of x, let's call this phi of x, right? So what are the changes I can make in x that truly do not change the output? So I can take every row and shift it independently, right? So basically I can start to, basically it's almost like you take an image, you cut it with scissors at every row, and then you can actually shift every row separately, right? So you're completely destroying the joint dependency of information across the different rows, right? So in other words, it's not because the group can be separated into different groups, into different subgroups, that the action of this group on the input is going to be separable, right? So here there's really like a loss of discriminative power, right? So formally, you are indeed building an invariant representation. I mean, it's totally allowed to do that. But the problem is that you are going to become invariant to too many things, right? If you see what I mean. Okay. And so this kind of phenomena, of course, this is like a bit of a toy phenomena, but it's in a sense something that appears also in the scattering, right? So what we had before, right, is that what plays the role of like the different rows, right, that we are treating separately, is the same thing as for us, like going back to the scattering. If I look at these different outputs, so now these become de facto as different rows, right? So we're taking each of these things separately, right? So we could potentially apply a different deformation along each of these channels and get basically the same sort of stability. I think there was a question.
I had a question.
Yeah.
Regarding this construction of the representation, it seems to me that you have some sort of ill-posed representation by building it, composing different translations in this way that you propose. So isn't it? So how would you argue that this? If I criticize this construction as saying, okay, but because you are constructing this as a composition of two transformations, and then you are mixing this or separating these two translations, no, in this example, when you also or you were thinking of translations as a whole.
Right. So it's really like, yeah, you should really think that when you factorize your group, you should not also factorize your inputs, right? And this is the problem that happened here, right? So here we are essentially saying my input is composed of different channels or different coordinates, and I know that different parts of my group are going to act separately into different things, right? That's the example of the rows, right? If I have an image, I have different rows, and if I think that my translation has a horizontal component and a vertical component, well, that seems pretty nice, because then I can say, well, one part of my group is only acting each of the rows separately. So I can maybe just, take a very complicated problem of building invariant representations and break it into sub-problems, right? That look tractable. And the fact is that it does work, right? So formally, as you saw in this like one line, indeed, you have invariance. But you are also right in the intuition that this is like it's very dangerous, right? And the reason why it's dangerous is because you have made this assumption that I can process each row separately, right? So basically I can I'm assuming that maybe there's a group coefficient, right? There's a group member that can be different at every row. And so I'm disregarding the fact that in practice, when I look at my images, right, and I have a translation, the horizontal component of the translation is going to be the same at every row, right, by definition, right? There's no different horizontal component. So there's something that needs to be kind of joining these things together, right? And so, like in general, when you do this divide and conquer, right, and when you take this complicated thing and you split it into different subproblems, you are entering a dangerous territory, right? You should always ask yourself, okay, this is making my life simpler, but there's no free lunch, right? There has to be something that eventually at the end of the day might be a problem happening, right? And that's what we see in this example. But it's also something that we have in the scattering, in the scattering I presented, because remember our problem, right, is that we started from this X indeed. But at some point, at any point in the transform, we replace these inputs by this family of channels, right? We have this guy, and we have all the different wavelets. So, and we are, from what I said, because so that we can make our lives a little bit easier, we are treating now each of these things, right? Each of these images now is being completely processed separately, right? There's no communication at all in the scattering that is happening anymore between these things. So you should think about this as kind of like warning, right? This is really like the same warning sign that we see in this previous example when we treat every row separately. What if there's some joint structure that is affecting all these images together? How can we process that? All right, how can we be aware of that and maybe, avoid becoming too invariant? So this is really what motivates, right? So the construction of joint scattering representations. Okay, and so this we are going to just very briefly introduce what we mean by that. And so, okay, and so For this, we would just need to realize that the main mathematical ingredient in the scattering is this construction of a wavelet decomposition, right? We have a wavelet decomposition operator that we define in R or in R2, right, in this example. So for this, what we need is just like to consider like we need to use a wavelet decomposition operator over a compact. Okay, and so, and the idea is really, really very simple. Okay, and so, okay, so the idea is actually very simple, is that if I have x that is a signal that is, let's say, square integrable in some domain omega, and I have h that is a function that is integrable over a group. So basically, it's like a function that maps, it's a function that is defined over a group G. And G acts on omega. Then we can define the following operation, right? Then we can define like a convolution over a group. So basically, we can take an image, a signal that is defined over the domain, and convolve it with the filter that is defined over the group. And so now this is going to be a function that lives on the group. Right? So it's a function that is in the group. So we can write it. And so how is the, so, and you can see this is the kind of definition that it can only be, I mean, there's only one choice, right? So we have to integrate over the group. And now what we need to do, we need to integrate over the group, right? So we can put what's like a measure of the group. That's what's called the Har measure, right? This is the Har measure. Think it as the equivalent of a Lebesgue measure, but over a group, right? It doesn't matter. So now we have a signal, we have this function over the group, right? So we better put it here, h of g. For consistency. And now here, what we need to do is that we need to somehow combine x with g. But we know that g is acting on the domain. So in particular, it's acting also on the signals of a domain, right? So basically it means that g also acts on L2 over omega, right? By the lifting that we described a few times ago. And so this is basically now g times x. Right? Okay, so this is really you can verify. So we verify that this group convolution is the natural extension of like the Euclidean convolution that we saw before, right? So if you say G, that is the translation group. Okay, if you put the translation group, you know that this is like really basically is exactly doing the same thing that we have, right? And actually now I remember that the convention we had was that this is like this, right? So because G times X at U is G of G minus 1 times, right? If you remember. Okay. Okay. And so we are not going to go too much into the details, but let me just say a few things, right? Is that remember that we described like the way we used convolutions in the Euclidean case was to say that convolutions are all the linear operators that commute with the group, right? So here we have the same thing, right? Like a group convolutions are the only linear operators, linear G equivalent. Okay. So what it means is that if I take a G that is acting on X and I convolve it with H, I look at this output at G, I get the same thing as if I convolve X in the group with H. Then I evaluate the result at G prime minus 1. Okay, that's the same thing. So it really does the same thing as before. And so now that we have that, we can now use the same. So if we can define convolutions over a more general group, you might say, okay, now we can do the following, the same thing that we had your wavelet decomposition, this little Witten transform over R2. Now you can do it over the more like a bigger group and formally apply the same thing. So this is exactly what is done, like as an example, for the roto translation, right? So G again being the roto translation. Okay, so G is R2 translated combined with the rotations. Okay, so this is the translation of the rotation. So the first thing we do, right, is that we start from so that's our group. So we start from our single X of U, right? So X, that is L2 of omega. And omega, let's think that omega is that R2, right? Is a subset of the thing. So the first thing we do, right? Like the first day of the transform is the same, right? Like the first step is that we go from X to all the possible convolution, right? So we just do a convolution with all the wavelets at different scales and orientations. Okay, and we can call that, let me just use a definition, right? Is that now we can call UX. Now is a signal, so I can just think about this as UX. So now I can, instead of thinking U of X as a family of feature maps, right? So that was like a collection of images, right? That's what we saw before. Now I'm going to see it as an image over a bigger domain, right? So I can just think about this, right, as a function of, let's call this U tilde, right? So U tilde has different coordinates now, right? So now this is the previous spatial coordinate. Then I have the scale of the wavelet, right? Like that is indexing the different channel, and the same thing, the orientation. Okay, so basically this is like the spatial coordinate. This is the scale, and this is the angle. Okay, so just to make clear what I mean, right, is that if I look at the collection of these images, right? So I'm basically thinking as a family of signals that are indexed by space. But I can also think it as a single image, right? As a single image. But instead of like the pixels being indexed only by spatial coordinates, now the pixels contain space, but also, of course, the indices that tell me in which of these channels I was in. Right, so we are introducing this kind of like a grid structure, if you want. It's a more general grid structure, right? As it turns out, this is really starting to have this roto translation structure over the image. Okay, and one thing that is the key point, right, is that observe, like the observation. Is that we have equivariance with respect to the roto translations. Okay, so if I have a G, there is again like a translation component and a rotation component. Then I can take the output of my transformed image, and if I evaluate it at these coordinates, I can now relate the coefficients in the first layer of a roto-translated image in terms of the coefficients of the original image. Now I need to see how this group G, how this group element transformation G is changing my coordinates. So obviously it's going to change the translation part. Yeah? How is it going to change my translation part? Well, that's going to change it by the way the roto translation group is acting on my input, right? So this is something going to be like this, right? If you remember, it's going to change, it's not going to change the scale, and it's obviously going to change the angle, right? So in other words, because I have this filter bank in Wavelet filter bank that contains all the possible rotations, like if I rotate the input and I apply a wavelet that is rotated, you can see that I can recover, right? Basically, I can relate the wavelet coefficients of two images that are one is rotated version of the other, just because my wavelet filter bank contains all the possible orientations, right? That's actually an important property. So now what it means is that formally, now I can just treat it as a single image, right? There is an image that is defined of a bigger group, right? So now I can just define, so now, rather than having a collection of signals, x lambda in L2 omega, we have a single signal in L2 of the group, right? Of omega in the group. Okay? And so we can use now, in the next step, we can just treat it as use the same idea, but instead of using a wavelet decomposition that is only defined over the grid, we can use a wavelet decomposition that is defined over the group, right? And so, so we can then process it further using a wavelet, basically a wavelet decomposition translation. Okay. And so there's other, and this has actually improvement, right? So like, what is the impact of this? That you have more discriminative power. With no loss of stability or impact. Okay, and so this is something that I illustrated for the rotor translation group, but there are other instances where this also has been working, right? Other instances where joint scattering has helped. So, for example, in the time frequency for audio speech, that's a work by Joaquin Anden. And also for rotations in 3D using a solid harmonic scattering for a molecule. This is a Eikenberg. Okay. All right. So, as it turns out, any questions? Good. All right. So, I wanted to talk a little bit about leave time to talk about open problems, etc. Let me just now say a few things about how we take this thing and generalize it beyond these examples. Okay, and so the point is really, and let me just try to be a bit brief, but try to give you a little bit the main directions. This really like really following this path of how can we make this thing a bit more general, right? So can these ideas give us like a general way of thinking about problems where we have this invariance, stability, keeping information that, you know, that might, even beyond these examples that we have described, right? It's like from Euclidean to, let's say, non-Euclidean stability. Okay, so, and let me just try to precise what I mean, right? Is that so far we have considered a very simple setting with a fixed, we have considered a fixed domain, omega, for example, that have global symmetries. That we model with group transformations and associated signal deformations. Okay, and so, and this we have used it for the domain being the grid, and also if you want, this stretch where we have looked into applications where you have like translation and rotation, right? So this is something that you could imagine applying for like signal defined over the sphere, for example, right? At any place where we can formally define this notion of group convolution. The thing is that there are many applications where we cannot assume the domain to be fixed, right? And for example, the things are like examples that I think about this, right? So that could be in network data, chemistry, or biology, in computer graphics. So in these examples, there's no domain that is fixed. But still, the domain has some geometric structure. Okay, so the point is that now, like generally, it's not a fixed domain. Basically, we go from right. So basically, but still, define let's say intrinsic operations with just deformations or global symmetries. Okay, so the point is really to let's see what I can say without going too much into the details. So, like, just to give you like the gist of it, right? So, right now we have seen deformations on the form like that. I have my domain that is always the same, and I have some signal over a domain, and this signal over a domain I can deform it, right? By just applying a certain diffeomorphism. So now what I wanna say here is that we can think about like a more general domain, for example, like a graph. So that's my new domain. Let's see. So now, rather than having this graph that is fixed and deforming signals over a domain, I can do the opposite. I can take this graph and I can change the graph a little bit, right? So there's a notion of deforming the domain itself, right? Basically, it's like from deforming signals over a fixed domain to deforming the domain itself. Okay, and so the point is that you can actually define. We can now take this notion of deformation and also use it as our prior for building good representations, right? So if you have now, let's say, a function that you want to extract information from a domain that looks like any graph like this, you might say, okay, I want to have a representation that if the domain changes a little bit, the representation changes a little bit, right? That's this natural extension of the stability. And in particular, there's transformations I can make to the input that do not change the domain. In the case of a graph, I can take the nodes of my graph and permit them, right? I have the same graph. The graph is an object that doesn't care about the order in which things are presented. So this means that the same thing, the same way that we had these kind of global symmetries, right? In the previous case was translation. Now we also have this notion of like global symmetries, but in that case, they really come from how we encode, how we embed the information in the domain. Okay. And so there's a big sense that there's some kind of like a unification, right? There's many of the ideas that we have introduced for translation that indeed are general ideas, right? And maybe just to give you a hint of what I mean, maybe just like have a diagram, right? Where I have a, we can think about like different domains in which the data lives. And so the first domain, you could imagine that's like a simple one. There's like a grid. We also saw today, without too much pain, how to go from maybe like a grid to a general group where we can still define the same architecture, the same convolutions, etc. Then we can also think about more general domains that involve the graphs and sets, right? And that's the idea that I have. So graph like that, or even another kind of domain where we can apply the same ideas, think about manifolds or meshes. So this is typically, think about an example where you have some structure in 3D, maybe, maybe like a shape, like some industrial application where you want to model, maybe like the design of a car or something, right? So the way it's represented is with a surface, right, with a manifold. And so we can have a notion of symmetries on these domains. So in the case of the grid, this is the translation group. Okay, that we can model as groups that are, in the case where I have real, like no infinite resolution is R, where I can have like cyclic groups. In the case of Lie groups, for example, like in this case, general groups, the group of symmetries are a bit more general. For example, in the case of the sphere, this is the group of all the rotations that leave the sphere invariant. In the case of graphs, as I said, the notion of like global symmetries, right? So what are the transformations that we can make to the input that do not change the structure? So these are all like permutations. So this is called a symmetric group. And here we have, in the case of manifolds, there's also like a notion of global symmetry. Like two manifolds are equivalent if they are related by a diffeomorphism, right? This is called the isometric group. So the same way that we have the symmetries, as I said, there's another key ingredient that is what is the kind of the neighborhood of the symmetries, like what is the deformation structure? So here, the right notion of deformation is to deform the signals, right? So we can deform the signals by a diffeomorphism, right? So we have a signal that goes from the domain, and then we can take a signal and apply the deformation, right? If you remember, we apply the deformation with a diffeomorphism. Here we can do the same thing, right? So here we can deform the signals by applying a deformation using the same thing, right? So we have L tau of X of U, that is a certain transformation. Here in this domain, we can actually deform the domain itself. So in that sense, we can take a graph G, and there's something that we can associate with a G that is a kind of a distortion. And the same way that we introduce in the case of the stability for signals, we introduce like this deformation cost, right? We try to define what it means for two signals to be close, like to have a small deformation, something that we penalize the norm of the Jacobian of the diffeomorphism. So here it turns out that there's also ways where we can take two graphs and compute how far they are, right? What is the distortion between two graphs, right? For example, there's something that is called the Gromov-Hausdorff distance. Okay, and the same way we can also talk about a manifold and have a metric deformation, not like a distortion. Distortion in the metric structure. Another notion of a deformation that is very natural for graphics, right? In this case, for people who do computer graphics, is the notion of remeshing. So what does remeshing mean? So when you have a manifold like a surface, let's say you want to model in an industrial application, I don't know, like a table or a car. So typically you discretize this object, right? If you want to process it with an algorithm. So you discretize it with what's called a triangular mesh. So this discretization, right? You can have two ways to discretize the same object, right? So you would like the representation to be stable, right? Not to change too much if you remesh the object, right? If the underlying geometry is the same, you would like the representation to be stable with respect to remeshing. And so what are the kind of architectures, right, that people have used that really fall into this umbrella, right? So these are so of course here we have CNNs, RNNs. We of course have the scattering transform that as I presented. Here we have like the spherical CNNs, and also we have of course the roto translation scattering that I introduced here today. Here for graphs we have GNNs, we have the deep set, which is the architecture where you just disregard the edge structure, right? Just look at the nodes. And then we have this transformer, which is trying to infer the edge structure. And here we have models that use like a surface net, surface net, mesh, CNNs, it's like point net, etc. So this is really not trying to give like a super exhaustive list, but really just to convince you that these ideas of trying to understand or like to formalize these architectures, like that, what is important between one architecture and the other, this gives you a framework to think about these architectures, right? And maybe to understand key questions about these architectures that involve maybe how expressive they are and how stable they are, right? There's always this like a key trade-off to understand in all these architectures is this stability versus approximation. Okay, and somehow this trade-off is still driving the research, right, in many of the architectures. All right. Any questions before we start wrapping up with starting going into the closing remarks? No? Okay. So let me just try to provide like a couple of ideas, like a couple of things that I'm throwing out here as a closing remark for the whole class here. So remember that when we started, right, we started with this kind of axiomatic way to think about what it means to learn functions, right? We had this like decomposition of that, right? That we said that the risk, like the generalization error of some our estimator, like relative to the best thing that we could do, right? Like relative to the best in class, could be controlled with basically a term that involves approximation error, a term that involves like a statistical error, a term that involves optimization error. And so the situation, right, is that even for the simplest setup, right, for the simplest learning set that is supervised regression. And for the simplest neural network architecture, which is a single kernel layer, the current state of affairs is that there's still like very large gaps, like there's still large gaps between positive negative results. Because what do I mean by positive and negative, right? So this is more like a a jargon learning theory that says, well, positive results are guarantees that you can learn certain types of functions. Right? So these are more like upper bounds. Okay, that tell me that if I have that many samples, I can learn certain class of functions. And negative results are lower bounds, right? That tell me the opposite. They tell me that this problem is hard, right? So if you want to learn that there's certain structures, it's not going to be possible, right? Or that the best, I mean, there's no way you can do better than certain things. So when I say that there's a gap, right, is that there's still a big class, a big chunk of functions where they are not so nice to be covered by the upper bounds and not nasty enough to be covered by the lower bounds. Right? So basically, we don't know whether it works or not. Of course, we can always run the algorithm and check, right? And of course, there's a kind of a big at the theoretical level is still pretty much unknown. But of course, you could say, okay, I mean, if in the simplest setting we still have this gap, I mean, that's where the research should be, right? Like trying to fix this big problem. But of course, there's many other things to think about, to worry about, right? Is that besides closing this gap, there's of course like many outstanding directions, right? There's some outstanding research directions, right? But I think are interesting. So first is that, of course, you would like to understand how to go beyond shallow learning. In terms of getting this full control, right? Like when I say in this setting, I mean like a theory that understands everything, right? That has like a full control of all the sources of error, right? So in particular, we'd like to understand what is the role of depth in architecture, right? So for fully connected neural networks, depth provably improves the approximation power, but there's a big cost, right? There's the expense of creating kind of very exotic or very degenerate functions, right? Creating very exotic functions. So in other words, we demonstrate that depth is important, but we only demonstrate it for very, very restricted class of problems that are kind of beyond any kind of practical usability, right? And this is like a nice work by engineer, Tarski. Also some work that we did. Okay, so basically, you can indeed understand depth in terms of better approximation, but you are losing the battle, right? It's like there's no way you can relate this to any benefit, any practical benefit of neural networks. But for structured networks, right, the situation is very different. For structured neural networks, for example, such as the ones that we just described now, where we have a geometric domain, CNNs, the depth is loosely related to physical scales, right? So it can be like the scale in space or the scale in time, right? So in other words, in physics, PDEs, for example, provide a very natural source of compositional structure, right? So when you think about like the state of a system, complicated system after time t, you describe the state of the system. If you describe it with a PDE, you are describing it as a composition of small increments, right? Like the state of the system at time t can be understood by composing some update rule at different intermediate timestamps, right? So a PDE is a very general way to produce very natural functions that are very natural compositions. And so somehow what we need is to bring this into the focus, right? And try to understand the benefit of depth in neural networks, maybe using this notion, right? This physical notion of scale. There's also an interesting thing about understanding like the interplay between depth and optimization. So the depth of the network can be also related to certain choices of optimization, like preconditioning, and also like more fundamental properties. And there's a nice work by actually Catalan researcher, Enric Bosch, that is really doing very nice work at MIT on this kind of problem. And that's a very nice construction that leverages depth to truly learn certain classes of functions. Of course, this is for shallow learning, and there's a big world beyond supervised learning, right? So there's a bunch of very interesting math to be understood beyond, right? So this, I mean, unsupervised learning, reinforcement learning, more recently, if you want to call this like as self-supervised learning. Okay, and so again, here there's an interesting thing, because in the particular case of a probabilistic modeling, generative modeling, there's currently like a resurgence of physics-based models, right? So models that really try to poke into like exploit kind of fundamental physical principles, right? So for example, Gibbs distributions are also known as these energy-based models. And more general, more recently, also like this notion of like a diffusion-based modeling, with an idea that is kind of very very natural, which they have some some data distribution. And I'm going to connect it somehow with a noise distribution. So there's a very natural way to do that, right? Is to add noise to your data, right? That's actually a diffusion. And so in physics, we understand very well, right? This is an inverse come-over of model, right? So there's another kind of reverse mode, right? Which is the inverse diffusion, or like the forward come-over of model. So basically, the idea in words is that it's very easy to take something that has structure and remove the structure, right? By adding noise. So there's recently a bunch of interest in trying to like generate images by learning how to invert the diffusion, how to do noise, right? So so this is where the learning happens. So this is a way to generate models from the data. Right? So this is of course like a very fundamental physics principle, and so understand how neural networks can help in this problem is something quite interesting and pretty much open, right? And of course the list can go very. All right, so I left a few minutes now. So as I said, what would be great is to do now like a round of table for those of you who want to participate, to just share your impressions, where you're at right now in your research, and what is the thing among the things that we talked about during this class. Is there something that that you're interested about particularly, so maybe we can keep in contact for the future.